Hey everyone, looking at class number 8. I don't have my document camera with me. Unfortunately, I forgot it. So anything that has to do with a protractor or a ruler, I'm going to be dictating. If you're not really sure how to use your protractor and ruler, please look at the videos for classes 6 and 7 where I go through it. All right, so let's get started. Our goal for today is to add vectors visually and to add them using protractors and rulers. So it says, draw the vector resultant of each pair. Use a ruler to ensure that they are straight. So for starters, why doesn't the order we add them in actually matter? Because we say that vector addition is commutative. So let's start adding these. It helps a lot to label them A and B. So I'm going to do that right now. Actually, I'm going to label all of them A and B. Does it matter which one is A? No. Doesn't matter which one's A, which one's B. As long as they're labeled, because we're just going to refer to them. Makes it easier to talk about. So let's start by drawing vector A. Now, when you redraw vector A, make sure it's basically the exact same direction and basically the exact same length. That's really hard for me to do here because I don't have a ruler or anything, but it's pretty close. Vector B points to the right, excuse me. Now it's important to line up vector B tip to tail with A. So it looks something like this. So we have vector B here. Our resultant goes from the tail of the first vector, so in this case the tail of A, to the tip of B. Now one thing a few people say is, wait a minute, that's tip to tip, that's tail to tail, that's not good. Well, no, tip to tail only refers to the two vectors that are being added together, in this case A and B. Okay? Now what if I wanted to add these a little bit differently? What if I wanted to draw B first? So I could draw B first. Make sure it's about the same length and about the same direction as B there. Mine's a little bit off, but that's fine. And vector A is tip to tail with B. Still the same direction, still the same length. I'm going to move this over a little bit so that it's still on the page. Our resultant goes from where we started. Oh, I didn't want to do that. Our resultant goes from where we started, so the tail of B, to the tip of A. Notice our two resultants are basically the same. They're a little bit different in size because I didn't measure anything out, but they should be basically the same. Now for the next ones, what I'm going to do is I'm just going to draw them one way, but it's up to you to determine, if the way you did it works. But regardless of how you do it, your resultant should be basically the same size and basically the same direction as mine. So let's add these two vectors. So I'm going to draw A first and then B. So A goes down to the left. And B is tip to tail with A. It goes this way here. Now check your work. You can't make mistakes if you check your work. So is A pointing the same direction it was before? Yes. Is it about the same size? Yes. Is B about the same size? Is it about the same direction? Yes. Are they tip to tail? Yes. So my resultant just goes from the tail of the first vector to the tip of the second vector. Now the last one here, you can kind of see how if you actually just like slide B down a little bit, they could be tip to tail, and you could draw your resultant vector pointing to the left. That's one way to do it. But I'm going to keep consistent. I'm just going to draw A first. So A goes up and to the left. Is that about the same size and direction as this vector A? Yes. Now look at vector B. I have to draw that tip to tail with A. So I can draw it down and to the left. Is that about the same size and direction as B? Yes. Don't flip the arrows. A lot of people get in the habit of flipping the arrows. No one said you're allowed to do that. Don't do it. So our resultant goes from the tail of the first vector that we drew to the tip of the second vector. That's my resultant. So what does this mean physically? Why don't we just do all this? Well, picture A and B. Let's say they represent force vectors, okay? A is a force pulling up and to the left. B is a force pulling down and to the left. When both of those forces act on an object, which way does it get pushed? Which way does it move? There it is, the resultant. Moves straight left. Or we can think of a different way, different vectors. Let's say A is the velocity of an airplane. B is the velocity of the wind. when we bring them together, what direction is the airplane going to go? It's going to go this way, the resultant. Okay, that's the magnitude of the resultant velocity and the direction. All right, so this should say, it's a little bit of a typo. This should say, look at the question below. So the question says, why can't we add the vectors the way they are now? So let's just read the question real quick. It says, the diagram below shows a resultant vector r. Which diagram below represents a pair of component vectors a and b that would combine to form resultant vector r? All right, so we can't add any of them the way they are now because they are all tail to tail or not. They must be tip to tail. Must be tip to tail. So we have to move these around, okay? And we have options to do this. I'll tell you right now that choice 1 is the answer, and we'll see that in just a moment. So these are tail to tail, A and B here for choice 1. We have to pick to move one. Let's move A. So I'm going to move A. I'm going to redraw A so it's tip to tail with B. And it's going to point the exact same direction, and it's going to be the exact same size as it was before. My resultant goes from the tail of the first vector to the tip of the second. There's my resultant. But what if you wanted to move B and not A? So notice this points up and to the left. That's our answer here. What if you wanted to move B and not A? You'll get the exact same answer. If we move B, B points straight left, so now it's tip to tail with A pointing straight left. Goes from the tail of the first vector to the tip of the second. There's my resultant, still pointing up and to the left. So it doesn't matter which one I move. I'm going to move B for all of them, though, just to keep consistent. So let's check out this choice here. So I'm going to erase B, point straight right, and I'm going to put it tip to tail with A, point straight right, B. My resultant goes from the tail of the first vector to the tip of the second vector, so it points up and to the right. Let's look here. These aren't tip to tail either. So this is a little bit strange to think about. But if I get rid of B and I line it up tip to tail with A, notice how, well, it looks kind of strange. Well, this would be like if you walk to the left 10 meters and then to the right 10 meters. What's your displacement? What's your resultant displacement? It's going to be 0. This is the 0 vector. You can't really draw it. It doesn't really have a direction. It's just 0. This would be the answer choice to part C. Now let's look at choice 4 here, and that's actually the work we have to do for here. So we have to move one of them. Doesn't matter which one you move. So I'll draw A first. I'm just going to draw it over here. Points up. B points up and to the right, something like this. My resultant goes from the tail of A to the tip of B. Okay, it's as simple as that. Don't overcomplicate this. Don't change the direction of the vectors. That's really important. And don't change their size. The two vectors that are being added together have to be lined up tip to tail. If you do that, you'll never make a mistake. Okay, you'll never make a mistake. And then the resultant goes from where you started to where you ended. That's it. Again, I can't emphasize enough. Don't make it any harder than it has to be. This should be easy. All right, so for this next one, it says John walks 12 meters. I want to emphasize that John walks 12 meters in a straight line. And then he walks 4 meters in a straight line. I should have mentioned that. Is it the same straight line? Well, no, it could be any direction, but whichever direction he picks, he's walking straight. So it says, which could be the magnitude of John's displacement? So this is a process of elimination question. How do you think we should go about doing it? Well, let's figure out his maximum displacement first. Like, how far could he really get away from where he started? Well, if John walked 12 meters this way and then 4 meters in the same direction, that's as far as he could possibly get away from where he started. That is a total of 16 meters. So there's no way John could have walked 20 meters, or there's no way John can be 20 meters away from where he started. That's what displacement is. What's the minimum result that John could have? Like, how close can he get back to where he starts? So let's say John walked 12 meters in one direction. And he said, okay, I want to try to get as close to where I started as possible. Well, that means he would have to walk backwards 4 meters. How far is John from where he started? Well, it looks like he's a total of 8 meters away. Okay, So there's no possible way for John to get back to 3 meters or to 7 meters. So the answer must be 11 meters. So what path did John take exactly? Well, you can use some advanced trig to figure that out. But let's say maybe he walked 12 meters this way, then he turned and kind of walked at an angle, something like this, 4 meters. I don't know exactly what he did, but it looks maybe something like that. Okay, so there's just a ballpark of what he may have done, but no guarantees there. So for this next part, what you need is a ruler and a protractor. So get those out now. You must do this one with a ruler and a protractor. The trig that you need for this is pretty advanced. I think it's like law of cosines or something. So use a protractor and a ruler. It will make your life so much easier. Okay, trust me. So the scale diagram below represents two forces acting concurrently on point P. Okay, so there's force A with a magnitude of 32 newtons and force B with a magnitude of 20 newtons. You don't have to know what newtons are, just know that it's a unit that represents force. The angle between the direction of the forces is 120 degrees. So we have to determine a scale first. So I think it's easiest to measure this 32 Newton vector. So take your ruler and physically measure this 32 Newton vector in centimeters. Okay, I have to double check what that is equal to. I think my class 4 or 5 has it. They measured it to be 5.5 centimeters. Okay, so let's measure that out. This is 5.5 centimeters. And I'm going to write it out actually in a few places. This is 5.5 centimeters. So to make my scale, I know that 32 newtons equals 5.5 centimeters. Now, I always like to get a 1 in front of the centimeters, so what I'm going to do is I'm going to divide both sides by 5.5. What does that come out to be? I think it comes out to be about 5.8 newtons equals 1 centimeter. So there's our scale. Okay, there's our scale. Now, the question here says, why do we have to move one vector? It's because we have to be tip to tail. Must be tip to tail. These are not tip to tail right now. They're tail to tail. No good. I got to move one of them. So the question is, well, which one do I move? Think about this. Vector B is a little bit challenging. If you were to redraw vector B tip to tail with A, it would look something like this. You have to get that angle just right, though. And that's a little bit annoying and not impossible, but it would involve more work to do it right. So what I would recommend doing is moving vector A, because it's a straight up and down arrow. So you can use a ruler, and you can just draw a vector straight up. Now this represents A. It should be a straight line, exactly 5.5 centimeters. I know mine's a little bit exact, it's not exact. 32 newtons, 5.5 centimeters. This is vector A. So this vector A is gone. So my resultant goes from the tail of the first vector to the tip of the second. That's my resultant. So we need to do two things. We need to get the magnitude of the resultant in newtons, and we need to get the direction with respect to a horizontal line. What does that mean? Well, if there were an imaginary horizontal line, we need to get this angle right there. So how do we go about doing this? Well, we have to first physically measure this resultant. Get its physical measurement in centimeters. It should be to scale. Okay, let's see what my other class got for this one. They got 4.7. You might get something slightly different, but that's about right. 4.7 sounds pretty good to me. So the resultant, okay, magnitude, I'll write 4.7 centimeters. Is that a force? No. So converting it to these centimeters is just a tool to get the force. Don't leave it like this. You have to convert it back. Using what? Using our conversion factor. So we're going to multiply by 5.8 newtons over 1 centimeter. My centimeters cancel. Let's see what we get here. We have 27.3 newtons. Okay. Now to get the angle, you physically measure that angle there. I don't remember what it was. It was 50 degrees. So you'd have to physically measure that. Okay, so if you're not sure how to use your protractor, please refer back to class, I think 6 and 7, I went over it, okay? So the angle is 50 degrees, okay? So that's my resultant, 27.3 newtons at 50 degrees. Now this question we didn't go over in class, but I do want you to look at it. So it says an airplane traveling north at 220 meters per second encounters a 50 meter per second, crosswind from west to east. Okay, so it's pointing east, as represented in the diagram below. What is the resultant speed of the plane? So my first question is, why are they asking for speed and not velocity? Well, look at the answer choices. There's no direction on the answer choices, right? No direction on answers. For these to be velocities, what it would have to give us is, let's say, 170 meters per second east, okay? It would have to give a direction, and it doesn't. So that's why it's asking for speed and not velocity. So it says, draw your vector addition sketch in the space below, label the resultant. So let's draw one of the vectors first. It does not matter which vector you draw first. I really want to emphasize that. So let's work, I don't know, left to right. So I'm going to draw my 50 meter per second vector. This won't be to scale. Now I have to draw my 220 meters per second vector, still pointing straight up, and it's got to be tip to tail with the 50 meter per second. So there's two ways I can do it. I can draw it here, 220, looks tip to tail to me. Or what I can do is, let's see if I can move it. No, I can't move it. Or what I can do is I can draw it tip to tail down here. Oh, that doesn't work there. I'll draw tip to tail down here rather. Are these tip to tail? Yes. Are they facing the same direction they were in the picture? Yes. Okay. I liked it the other way I had it, so I'll start with that. Again, pretend those are straight lines. So my resultant goes from the tail of the first vector to the tip of the second. This is my resultant. So I have to show my math below to get the speed, which is the resultant, right? It's asking for the magnitude of the resultant speed. So I'm just going to do 220 squared plus 50 squared equals my resultant squared. So let's see, I'm just going to throw this in my calculator real quick and solve for R right away. That comes out to be about 226 meters per second. And if you wanted to find the angle, you could definitely find the angle right there. Okay, using some trig functions, just double checking my work there. Yeah, that looks pretty good. All right, so have a great day. If you have questions, see me in class, all right?